let's recall what the derivative is, and let's recall what the definition of a C1 function is. Right. So as usual, U is an open set in some R M, and there is a function to Rn f, and A is some point in here. So f prime of A is a linear map T from Rn to Rn such that the familiar limit exists and 0. So of course, as stated, this does not make sense. At the very least, what do I have to do? Division by h does not make sense, so I have to put the norm here. Does it matter which norm I use for Rm?
No.
No. But remember that we are going to be using Cauchy-Schwarz for various estimations. So we will normally use the Euclidean norm. Okay. And for operators, we will use the operator norm. Very well. Do I need to put norm at the top for the numerator?
We don't have to.
We don't have to, but we can, right? The meaning changes. The 0 on the right hand side will be a vector or a scalar depending on whether I do not put the norm or whether I put the norm. But this is okay. Okay, so let's also recall what is the matrix of with respect to standard bases of Rm and Rn. So what is this given by? Is precisely given by the partial derivatives, right? So let's write this down. So this is going to be the partial derivative of, so where we can write this down, f as component functions, and maybe, so because I'm going to be writing vectors generally as column vectors, so let's write as f of A is going to be a tuple of n real numbers, and each one of them is just a real valued function of. Okay, very good. And why like it? Let's also remember. So f is really just a collection of n real valued functions. And we have seen that f is continuous if and only if each one of the fi's is an ordinary continuous real valued function. And more general, and we got this based on what fact? That, so let us recall for limit as, let us say, x approaches some vector v of f of x, and let us say that is some value. So let's call it, let's say, b1 up to bn. So what did we see here? This is equivalent to saying what?
Limit fi of x tends to bi.
So limit as x approaches b of fi of x is equal to b. So one way is straightforward, because I can just if f is if f has a limit, then I can compose it with the projection function, which is continuous. And so the forward direction is straightforward, but the backward direction is also true, as we have seen. And we have used this repeatedly, and we are going to be using this today also. Okay, so let's write down the let's write down the matrix of this, and this is just given by partial derivative. So this is going to be del f by del x1 at A by del x m at. So this looks like a row matrix, but remember del f by del x1, f itself is a column vector of n numbers. So each del f by del x1 is a vector. So if I write this out fully, then this is going to be, the first column is going to be the partials of all the individual fi's. Right, with respect to x1. Of course, all of this evaluated at A, and likewise in each column. So the last one is again going to be all the partials with respect to x. Okay, very good. So in particular, remember that if, so in particular, if this is what we sometimes call the derivative, right? The total derivative. If f prime of A exists, then all partial derivatives also exist. All del fi by del xj exist. But now a tiny remark over here. Suppose f prime of A exists and f prime as a function is continuous. So this is what we said as the definition of, so let's write this. F prime as a function. So suppose in the above situation, f prime of A exists for all A in this open set U, right? Then we get a function f prime which to any element A in this open set assigns its derivative. So it is important to keep in mind where this function lands in. Remember, f prime of A itself is a linear operator. So this lands in the set of all linear operators from Rm to Rn. And as a vector space, this is really isomorphic to Rmn. Because you can identify every such operator with a matrix. Its matrix with respect to the standard basis. And so since the target is a vector space, in particular, it has a norm. All norms are equivalent. It's a metric space, you know. And we can talk about the continuity of this function. So say that we say f is in C1 of U, or in words that f is continuously differentiable if the function f prime exists, that is f prime of A is defined for each A, if f prime of A exists for each A, and f prime is a continuous function. So theorem is that f is continuously differentiable if and only if all partial derivatives exist so I should say here exist at each, no, sorry. Let's write it slightly differently. And are continuous. Okay, so all right. So what kind of gadget do I get when I calculate the partial derivative? Come on. So these are all functions from where to where? Hello, are you awake? Right. So, I'm evaluating these at every point. So the source of this is U, may not be all of Rm, but wherever F is defined. And the target of these, I'm just getting a real number, no, out of each one. So, okay, so maybe what we should do is just write down the call. What is the definition of del F by del X J at A? So since I'm thinking of this as a function, instead of writing a vertical line and putting A there, let me write A as an argument. What is this by definition? This is limit as H approaches 0 of what? F of what changes compared to the definition above?
We're only considering the EJ direction, so we're just adding H plus EJ.
Correct, exactly. So in particular here, H is a real number, right? And I'm going to therefore just divide by H. Okay, so we have laid out what we want to do. So let us see what the crux of the matrix is. A bunch of this is just easy, and let us try to identify where the real action is. So out of these two, is there any direction that is straightforward?
Forward direction.
Okay, so forward direction is straightforward, and part of this is just written up here. Okay. So we said that if f prime of a exists at any point, then all the partial derivatives exist at that point. This was a matter of just writing down. Because for the total derivative, I was allowed to add any vector, any small vector h to A. So in particular, I can add small vectors in a fixed direction, and the limit will still exist, the relevant limit. So that was all, that was it, that was there. But there is something more, right? This says that if f is continuously differentiable, that means that this function f prime, which is going from U to the space of matrices, if that function is continuous, then all the partial derivatives, well, I know that they exist, but they are also supposed to be continuous functions. Is that obvious? All right, let's take a look up here. I know that f prime of A exists at every point E. And what does that mean? That means that at every point of E, at every point of U, the matrix of this total derivative is given by this matrix that I have written over here. This matrix. That's the matrix. So this is happening at every point. Now I'm saying that the map that takes any A to this matrix is a continuous map. That is what the forward direction is telling you. So what does it mean that a matrix valued map is continuous? Do you see the recall part?
Each component is continuous.
Exactly. So, I mean, it may be written in a rectangular fashion, but it really is just a list of numbers, right, in Rmn. So, if this entire vector is varying, mn coordinated vector is varying continuously, then that means that every slot is a continuous function. That is what this recall thing said, no, which we have used several times. So, the forward direction is completely straightforward.
Sir, why can't we reverse the argument we just made? Like, can we just reverse it to get the backward
Correct.
direction?
So just think about it, and just think about what. So what is it that you would like to say? Can you make a precise statement? Think about this and think about what he's saying. He's saying that what the argument that we just said can be reversed, right? And it is indeed true that this can be reversed because the recall part, that is both forward and backwards. All right. So does that mean that the reverse is also obvious? Not quite, but it does give me something. So while I write down what we just said, think about this.
Sir, just a question. In the theorem, do we assume that f is differentiable in the RHS of the implication?
No, I do
Because
not. No, I do not. No, I do not.
so because we last saw that existence of partial derivatives does not guarantee the existence of a total derivative.
Exactly, exactly. So, but still, part of his comment is valid. So in fact, you know what? Let me just say. So in light of, so maybe let me just say, so this is 0 and 1. Or let's just say 1 and 2. So in light of 1 and 2, obvious thanks to 1 and 2. Now let's look at the proof of the reverse direction. And the observation that was just made is precisely the point. So we can say if we prove that, if we prove that so notice what the hypothesis is. The hypothesis is that all partial derivatives exist at each point and they are continuous functions. That's what is given to me. So before showing that f is continuously differentiable, I have to first show that it is differentiable. So suppose I do that. Suppose I prove that f prime of a exists for each a in U. Then I claim that it's automatically continuous. That if the function f prime, speaking in a sloppy way, f prime of a being a linear map is of course continuous as a linear map from Rm to Rn. But what I mean is f prime as a map from U to the space of linear maps from Rm to Rn is also continuous. And why is that?
Sir, if we understand that f dash as a function is well defined, then if all its components, it's like since it's a matrix valued map, if all its components are continuous, then it has to be continuous.
Right. So to show continuity of a function, remember that this function is the target of this function is the space of matrices m by n. So it's an mn dimensional vector space. So continuity of this function. Now again going back really to remark 1, but the backward direction. If all the component functions are continuous, then the entire function is continuous. And the hypothesis for the backward direction is giving me precisely that. It is saying that all the partial derivatives exist. Remember, I have to show that the total derivative exists. But if the total derivative exists, because then the matrix of f prime of A must be the Jacobian matrix, right? Because if f prime of A exists, then its matrix has to be given by partial derivatives. And all the components of this are continuous, because that's the hypothesis. But remember, there is a then part. And given that all entries of this matrix namely the functions so this is by 2. So let us say by so 1. Okay, so good. So we have made one reduction. Is that really the fight is the fight is in showing that the derivative exists. Now let us do one more thing. Another reduction. So we may assume that n is equal to 1. In other words, I have a single real valued function, not a tuple of this. And again, the idea is not difficult. We just follow our nose, because so reason assuming this case, in general, what do I have to show? I have to show that f prime of A exists, right? So not I have to. So what will I show? So in general, it follows immediately for f is equal to this column function f1 up to fn. What would f prime of A be? Remember, each one of the functions f1 up to fn is just a real valued function, right? So for that, I am assuming that I know the result. So in that case, what would be f prime of A? So if this is difficult, then it's only a semantic difficulty. Okay, what is the derivative of f1? I'm assuming that it exists, which is where the main fight lies. But f1 is just a single real number, which is a function of m real numbers. So if I calculate its derivative, what kind of matrix will it be? What will be its dimensions?
And this is going to be a row matrix.
It's going to be a row matrix, correct? Because the map is from m dimensions to 1 dimension. So the derivative will also have the same, right? So you see f1 prime of A is a row matrix. And likewise, I'm going to have all of those row matrices. And what is f1 prime of A? By the way, f1 prime of A is going to be, this is slightly sloppy notation, maybe not. So f1 prime of A is just going to be del f1 by del x1 all the way up to del f1 by del xm. All of those at And similarly for the last one, del n is 1 at A. So I said we can see this easily. Why is this easy? Well, look, no. So we can see easily that. So let's call this P. Well, check. What do I have to check? Limit as h approaches 0 of f of a plus h minus f of a minus th divided by h is equal to 0. Well, but what is this? Just look at what is on the top. What is f of a plus h? Remember what f is. F is just a bunch of real numbers, real valued functions. So f of a plus, evaluating f on a plus h just means evaluating all the functions f1 up to fn on a plus h and sticking them together. So this is f1 of a plus h, fn of a plus h. That's what that vector is. Let's just get rid of the limit so that. And then what is f of a? That is really f1 of a up to fn. And what is t of h? Just notice. So h is a vector, h1 up to whatever, right? h1 up to hm. So what does it mean to take t of h? Look at the matrix of t that I have made. That also needs to be a vector with n components, right? What is its top component? What do I write?
Gradient of f1 dot with this.
Right, but I don't really need to write this as a dot product. Just think about this.
f1 prime a h.
Right. So you see f1 prime a is a row vector, right? When I multiply that row vector by the column vector h, that's precisely what a matrix multiplying a vector is the same thing as every row of the matrix multiplying the vector and giving me a number. So this is really f1 prime a h up to fn prime a h. That's what the top is. And then I am going to just take all of this and divide that by h. So do you see which way this is going?
Yeah, now we can break the limit into components.
Correct. So I want to show that this limit is equal to 0. And limit of a vector, this is a vector valued function. So its limit being 0 means that in every slot the limit is 0. But I have assumed that the result is true for each one of the real valued functions, right? So limit as h approaches 0 of this is equal to 0 because in each slot the limit is 0 by the n equal to 1 case, which we have assumed. And we'll prove now. Okay, so good. Any questions so far? The point of all of this was all of this came for free. There was nothing much to this. The real action starts now. Okay, so good. So, okay, so let's do this properly. So proof in case n equal to 1 of of the fact that, let's write down exactly what we are proving. Always good to remember what the question is before launching into the answer. As Amir Khan told us in 3 years. So proof in the case n equal to 1 of the fact that if, so there is only one f now, there aren't f1 up to fn. So if del f by del x I, or did we call this j? Yeah, j. For j equal to 1 to m are continuous functions from u to r, then f prime of a exists for each a in. So this is what we are proving. All right, very good. So that is, so what is there to show? So i.e. see, if f prime of a exists, then is there any is there any mystery about what it has to be?
No.
No, because we know that if f prime of a exists, then its matrix has to be given by the partial derivatives. So we know the answer. We just have to show that the answer is correct. We want to show that f prime of a is, and what is the size of this matrix now? Remember, the function is from m dimensional space just to R1. So again, the matrix is just going to be a single row. So we want to show that f prime of a is equal to del f by del x1 at a up to del f by del xm at a. This is what it has to be. So let's call this p. Well, I know exactly what to do. I have to show that limit as h approaches 0 of f of a plus h minus f of a minus ph divided by the norm of h is equal to 0. Very well. So we just have to now plug in and then see what happens. And at some point we have to do work. So far we have done essentially no work. All right. So what is pH? So, okay. So, all right. So we are fixing. So fix. So let's write this down. I have fixed A1 up to AM. I should have really written it as a column, but maybe transpose. Okay, how about this? We will use both notations. As long as I'm not multiplying things, this should be okay. Because writing columns takes a lot of space. Okay. So let's look at all the things in there. Now I want to calculate what all of these quantities are. So I really should take H also to be something. So let's look at slots of H. H1, H2 up to Hn. So what is pH? That is something that is written up there, right? It's part of. So TH means I have to take this row matrix of partial derivatives and evaluate. So let me really just write transpose here. So TH means I have to multiply this row vector with this column vector. So what is the result of doing that? Well, let's just write this down. This is just del f by del x j at A times hg, and I'm taking sum over g. Okay, let's bring in the dot product. This is really the same thing as now I'm going to write these del f by del x1 up to del f by del x m, all of those evaluated at E, and the dot product of that with h. So h1 up to h m. This is going to be useful for later on for forming estimates. Okay. Now let's try to calculate this f of a plus h minus f of a, right? So let's just write this. So f of a plus h minus f of a. And now here is sort of the notice. The real action is starting now. So this is f of a1 plus h1 up to f of an, sorry, f of, not f. The f is just evaluated at the vector a plus h, which is up to am plus hm minus f of a1, a2 up to an. Here now comes the bright idea. You see, I have to take this difference between the f values, subtract the dot product of that, and I have to show that the limit of that quantity divided by the norm of h is 0. So really what I have to do is I have to bound the, so want to bound the right. So this is what I want to do. I want to bound the numerator. Okay, so how to motivate this now? This is very nice. Okay, so the idea. In terms of partial derivatives, using the mean value theorem. Okay, so what is the idea? Now I can say, wait, but to use the mean value theorem, we proved two versions last time, the multivariable versions. To use mean value theorem, the function has to be differentiable, whereas we are trying to prove that the function is differentiable. So I really don't have the mean value theorem for f, but I do have mean value theorem for some. Namely, if I slice this function in any one of the principal directions, in other words, if I fix all the variables but one and only let that variable vary, one of the x's, then I know that then this function is just of a single variable. And I know that each one of these single variable functions, by fixing the values of the other coordinates, is continuously differentiable, because my hypothesis was that each one of the partial derivatives is continuous on all of you. So I have fixed this a. At this a, if I slice this u in any one of the, if I go in any one of the principal directions. So at a, I just step in the x1 direction, or I step in the x2 direction. In all of those directions, the function varies, the function is differentiable, and the derivative is continuous. So for each one of these one variable functions, I can apply the mean value theorem. So can say the ordinary one variable version, which is applicable because each del f by del xj is continuous. Okay, so this is sort of a this is going to be our idea. All right, but what this means is that I can step only in one direction at a time. So this is what I do. Right? So f of let's continue with this over here. So let's think of starting at a1, a2, a3. That is the point A, and going to the desired point a plus h. But I cannot go in one shot. So if this is A, A equals A1, A2, A3. Then I want to go here. I want to go to the end. Okay, let me not draw that. I first go in the x1 direction. So, and you see, I want to end up at the, so for simplicity, let us just draw the case m equal to 3. Okay. So in the first case, I want to always step in one of the principal directions. And I want to end up at the point a1 plus h1, a2 plus h2, and a3 plus h3. So in the first step, where should I go? How much should I travel in the x1 direction?
H.
Right. And you know what? I did not. So let's draw a larger picture. So here is. So from A1, A2, A3, which is A, I step to A1 plus H1, A2, A3. Okay. From here, I step in the, so this is a right angle. I'm trying to draw a three-dimensional picture here. Then I go to A1 plus H1, but I add H2 to the second point. And now the third one is, and then finally I go up to, I hope you see this as a three-dimensional picture. So this is also a right angle. And I go finally up to A plus H, which is A1 plus H1, A2 plus H2, and A3 plus H3. Okay, very well. At this point, you should be objecting. So I want to use the mean value theorem going from A up to this A1 plus H1, etc. So use mean value theorem, MVT in each segment. Okay, so if you do not object, let us just go on. And then, all right. So remember, what is it that I want to bound? I want to bound f of A plus H minus f of A. So that difference, I'm going to break it up into three parts. So there is f at every point. So I start with f of A, see how much it changes to go up to the second point, then see how much it changes to go up to the third point, and then the final point. So the way I'm going to write this is as f of A plus H minus f of A equals. So this is going to be, so I will first start with the minus f of A part. So minus f of A. From this, I'm going to go to f of A1 plus H1, and then A2 and A3 are the same. But then I have to cancel that out. So I will subtract that f of A1 plus H1, A2, A3. And I have stepped up to A1 plus H1, A2 plus H2, and A3. But I don't want that either. So I go to the last one, which is f of A1 plus H1, A2 plus H2, A3 plus H3. And minus the previous one, the previous cluster. So A1 plus H1, A2 plus H2, A3. So, so I'll just make a remark over here, which is that I'm just writing this down for general situation is completely analogous. It just prevents me from having to write dot, dot, dot. Okay, so what do I get by the mean value here? So notice that in the first case, I have this function on this segment. I'm restricting the function f to this segment. This function is differentiable, but the derivative is also continuous, because the derivative when restricted to this is precisely the partial derivative. I'm sorry, that did not come out right. What I'm saying is that if I take the restricted function and if I calculate its derivative as a function of x1, then at each one of these points, the derivative exists. Because that's precisely what the partial derivative with respect to x1 is at that point. Just look at the definition. What is the partial derivative? So instead of a, I have any point between a and then the next a plus, a1 plus h1, a2, a3 on that segment. At any point, this function is, this limit exists. That's what we are told. And not only that, this partial derivative is a continuous function. So what do I get by the mean value theorem? This first term, f of a1 plus h1, a2, a3 minus f of a. By mean value theorem, what do I get? Okay, so this is sort of the critical point in the proof. So you have to understand this. Okay, so maybe let me make notation of it. So let us say g of x is equal to f of x a2 a3. This is a continuously, okay, so even before writing that, at any prime g prime of x, just as an ordinary real number, what is that?
On the first partial of f.
Del f by del x1. At which point?
At x minus h?
Well, the point has to be in the
Sorry,
dimension, right? Yeah. So this is going to be at
X
the
minus
point x, comma a2, comma a3. Correct.
Yes, yeah.
And so we can say that g is a continuously differentiable function from where to real numbers? I'm applying MVT, right? So I want this to be a function from a1 to a1 plus h1. Right? I'm just holding the so I'm just looking at this segment. I'm ignoring the second two coordinates. In other words, I'm just precomposing with the function a1 to a1 plus h1. There is a map which is just sticking the coordinates a2 and a3. That's what I'm doing. The fact that the partial derivative of f is continuous in U is telling me that this composed function, where the domain is now a closed interval of the real line, is a continuously differentiable function, and therefore I can apply the mean value theorem. Yes. Do you agree, or is there a problem with this?
We don't really need the derivative to be continuous for mean value theorem, right?
No, we certainly do. So what is the hypothesis for the mean value theorem?
That the function is differentiable in the open interval.
On the closed interval, but the derivative has to be continuous on the open interval.
Okay.
Okay. So I don't particularly like the quality of silence here. So I claim that there is actually a little lie here. I have to say something to justify this.
So could you repeat the statement again?
Of what? The mean value theorem?
No, sir. The one, like the one you said just a while back, my internet cut out, so I'm not sure exactly what it was. The one that you're saying has a lie in it.
No, so what I'm saying is what I have written over here, there is some problem here, a small problem which I have to fix. You see, where is the function f defined? The function f is defined on an open set. Yeah. And A plus h are both points in this open set. So why can't, I'm saying I'm restricting this function to the path from A to the first point, to the second point, and then the third point. Now my question is the following. What if my open set is something like this? You see, there is a problem, no? Because I want to restrict f. I want to evaluate f on every point in this path. If my open set is of this type, then I will not be able to do that.
So by choosing h small enough,
correct. By choosing h small enough so that what happens?
the whole path lies inside the open set.
Correct. So what do I have to do in order to see this?
First, choose a ball around A.
Right. So let us do this.
Then we will make the norm of h less than the radius.
So let's okay. Choose r greater than 0 such that a ball of radius r around A is in U, and restrict h to values, to vectors, restrict, basically now just restrict it to small okay, so such that norm of h is less than r. So this entire ball is contained in does that ensure that the path, that all of the path stays in U?
I think we need h a bit smaller.
No, I think it is okay because you see this ball is convex.
So what norm are we using?
Any norm is okay. I mean, of course, we are using the Euclidean norm, but here's a small exercise. The ball is convex. So let's write this down. So as BR, no, let's not do this. Okay, fine. As BRA is convex.
Oh yeah, sorry, sir. I thought, yeah, I got confused. It works, sir. Sorry.
The entire path is in U. So this is also something that one needs to remark. So what is the point? Okay, notice that the distance from A to A plus H is less than R. Therefore, the distance from, just look at triangle inequality. The distance from the distance from A to any one of the intermediate vertices is also going to be less than R. Therefore, all the intermediate points are going to lie in the ball. And a ball is convex in any non-linear space. You can just see this simple exercise. Therefore, since the endpoints of any segment of this path are in your set, in your ball, therefore in U, therefore the entire line segment lies. This is what ensures that I can actually calculate that the function that I've defined G here is really a function on the entire interval. And by the hypothesis, it is going to be continuously differentiable. So what does the mean value theorem give me now? All right, what is the length of this segment? So let's look at the first segment. Let's look at this one here. What is that equal to? By the mean value theorem, it is the value. So that function is G of, that is G of A1 plus H1 minus G of A1. So by the mean value theorem, this is going to be the derivative of G, which is just del F by del X1 at some point, right? Times H1. At what point? At some point in this path. So, so let's call this point something. So there is this point, and I'm going to call this okay, C1. But this is kind of a bad notation. So maybe V1, because it's really a vector, you see, it's not a number. So let's call this V1. Likewise, I'm going to get a point in between here called V2, and likewise a vector here called V3. Such that what happens? At V1 times H1 plus, so each one of the lines is the corresponding line. So plus del F by del X2 evaluated at V2 times H2 plus del F by del X3 at V3 times H3. So I can write this now as a dot product. Del F by del X1 at this in between point V1, del F by del X2 at V2. So you see, I have changed it from a row to a column. A row, row vector of the partial derivatives. That's what I'm going to claim to be the total derivative. But right now I want to write it as a column vector because I want to use Cauchy-Schwarz times just the vector H. So H1, H2, H3. Very good. So this is what I have. Let's write down the other term. So, or rather, let's look back. What was TH? That was also a dot product. But look, it seems to be the same, no? The dot product of partial derivatives with H. Is it really the same? No, it's not the same. So the difference is that, okay, so let me see if I can just do it this way. All right, can you see this? I hope it's not too small. Notice the difference between the two. The dot product at the top here, this one, and this dot product. Is it really the same?
No.
No. The point is that the partial derivatives are evaluated at different places. In the top, they're all evaluated at E. Here, they're all evaluated at some in-between points, V1, V2. Right? Okay. And what is the quantity that I need to calculate? The quantity that I need to calculate is the difference between these two. The bottom quantity, which is f of a plus h minus fa, and the top. So let's get to it. So putting it together, f of a, okay, I should really write this down very carefully. So we here, this is important to note. V1, V2, V3 are functions of h. They depend on h. Right? So let's write this down here. So putting together, I get f of a plus h minus fa dh divided by the norm of h is really equal to 1 divided by the norm of h times. Now you see the first quantity is that top is the dot product that I have over here, and the second quantity was the dot product of a different set of partial derivatives, but also with h. So all put together, I simply get this is the same thing as dot product of h with something. For dot product, the order doesn't matter. H with what matrix? Del f by del x1 at v1, del f by del x2 at v2, and del f by del x3 at v3, and minus all of those at del f by del x1, del f by del x2, 3, subtract, but all of these now evaluated at. Okay, so now for simplicity, let me give some names to these vectors. So let's call this vector here P maybe, and this vector here Q. So this is really just so name these. So this is 1 divided by norm of h times h dotted with P minus Q. Okay, very well. Let's bring in Cauchy-Schwarz. So this is the same thing as 1 divided by norm of h times, what do I get for the dot product? Norm of h times norm of P minus Q. So which is just norm of P minus Q. We're almost there now. How do we finish?
As h goes to 0, v1 was less than h. Or rather, v1 was like in between. I don't remember the notation, sir.
Correct.
But
So I
v1
will go to the picture. So what we have, so upshot is that, remember what we have to do with this limit. So let me put a line over here. Putting together that expression here, what do I want to show? So want limit of this as h approaches 0 equal to 0, right? So I have bounded this quantity above by something. So if I show that the limit of this quantity P minus Q as h approaches 0 is 0, then I'm done. So as limit, not as, let me not be so rash, because we do have to justify. Yeah, is enough to complete the proof. But what is P minus Q? So P minus Q is, so okay. So what does it mean to show? But so this is, see, limit. After all, P minus Q is a vector, right? The norm of that vector going to 0 just means that all the components have to be to go to 0. Because the only way the norm of the vector will be 0 is that if the vector is 0. So this is if and only if P minus Q goes to 0, as H goes to 0. But this is really the same thing as saying, now look at all the components. What is the top component? Or each one of the components is really simply del f by del xj at Vj minus del f by del xj at A. But this is just true because
Vj is between Aj and Aj plus Hj, and Hj is being squeezed. Hj is going to 0, so V1
right.
Vj
No,
has to
okay,
approach
so
it.
good. This is fine. So what you just observed is that as the point H, this point moves close to A, the entire path is collapsing. So these waste stations, they also collapse into A, and so something that was on the segments also collapses. But that's not enough. But there is something more. You see, it is not enough to say that V's go to 0. See, what I have is that the partial derivative is evaluated at Vj and the partial derivative is evaluated at A. So each partial derivative, we know that, see, Vj is getting close to A as H goes to 0, but why should the value of the partial derivative, why should the difference between the partial derivatives go to 0?
They're
Right?
continuous.
Because they are continuous, right? And this is true. Because del f by del xj is a continuous function. So let's just finish by saying more formally. So formally speaking, what do I have to do? I have to show that whenever H is more formally, choose H less than delta such that this is the function that I'm bounding, right? So this function evaluated at B minus this function evaluated as this function evaluated at A is less than, well, you tell me what it should be less than for all B in the delta ball around A. That's exactly what the continuity of the function means. Yes. So I get to put any epsilon that I like. But which epsilon should I use? Now notice that each one of those points, each one of the waste stations, since I have chosen H itself to be within distance delta, all the points on the path, everything, the turning points and also all the V's, they're all within that radius. So what will happen? So when I put this B to be each one of the V's, it will also ensure the bound of epsilon. And if I say that this is one, epsilon by n, then this will ensure that.
Isn't it n? N is 1, right?
Oh, sorry. Sorry. So yeah, right. So I think M, no, probably. Just sorry, I'm missing my M's and N's. Yes, it is a function from Rn. Correct. So in the example, I took m to be 3, but the reasoning stays the same. And notice that now I'm going from A to B via, so many steps. No, so this is going to be all right. So just see that. Basically, what happens? You see. Notice this P minus Q is really a sum of m vectors. Which m vectors? I just take the respective partial derivative difference in each slot and put all the other slots to be 0. Correct? The way I have chosen delta, the norm of each one of these vectors, which is 0 in all but one slot. And in one slot, it is the difference del f by del xi from at vi minus del f by del xi at a. The norm of that vector, I have ensured that by taking h within delta, by h of radius at most delta, I have ensured that this difference stays at most epsilon by m. Now the norm of a sum of vectors is less than the sum of norms, less than or equal to. That's the basic thing. So by using triangle inequality, see that this ensures norm of P by Q less than epsilon by triangle inequality. So really a lot of it was just scene setting and just things coming for free. The key idea of the proof is remembering this picture and applying the mean value theorem in each segment. Okay, so we are out of time. Just give me 2 or 3 minutes because I want to give you work. Since I'm not going to be seeing you for an entire week, you will get work by email, but he is already somewhere. So this is what you should do. So do problems from Rudin chapter 9. I said all of them, but in particular, try to do these problems 5, 6, 7, 8. I will just say try 9 and 14. Okay. So what are these problems about? Let me just take a minute or two to let's go back to the statement of the theorem. Yeah. So we can ask several questions. Can we weaken the hypothesis? Right? So in the forward direction, can we say that if f is, if f just has derivative, suppose f just has a total derivative at every point. We already know that del f by del x, the partial derivatives then exist at each point. But do these partial derivatives need to be continuous? And the answer is absolutely not, because there is nothing multivariable over here. We can just take the one variable situation. If the derivative of a function exists at every point, there is no reason why the derivative needs to be continuous. And you've seen examples of that. Remember the function, whatever you play with sine 1 over x, right? X square sine 1 over x, etc. So in the forward direction, there is nothing really much to say. In the backward direction, suppose all partial derivatives exist at every point. Does that mean that the function itself has a total derivative? And the answer is no. In fact, what is true is the following. You can sort of here. And Rudin will tell you several examples, but let me give you an additional problem, an additional calculation. So in fact, do the following. So caution. This is related, but it's a somewhat different example. So define f of xy to be xy squared by x squared plus y to the 4. So f is from R2 to R. And of course, this is completely defined at all points except, I mean, this definition makes sense for every single point except the origin, right? Because as soon as even one of x or y is non-zero, then the denominator will not vanish. So I just have to define, so xy not equal to 0. And of course, at the, so, so 3 parts. Calculate all directional derivatives. In particular, del f by del x and del f by del y at each point. Okay, but just look at this for a moment. If I look at the origin, do partial derivatives exist? Come on, this is an immediate question. This function, so calculating partial derivatives, that means that you have to go in the x direction and y direction and calculate derivatives. What is this function on the x-axis?
0.
0, as it is on the y-axis, right? So at the origin, both partial derivatives are 0. But in fact, you should check that all directional derivatives exist at all points. The only point of interest is the origin. Everywhere else, there is no issue, right? Maybe we should really just why. And of course, the answer is going to be no. The problem is going to be at the origin. But now look at this question. This is f. And things get interesting at the origin, right? So please do this problem. All right. So for the midterm, we will have everything covered up until this point. All right. Including the examples that I'm assigning you, right? So the homework that I'm giving you is definitely included. The next thing that we do is, after the, so we will meet from not the next week, but we will meet the following Monday. And at that time, we will get to inverse function theorem and implicit function theorem, but that will not be on the midterm. Right? So, okay, good. So let's stop.
Recording stopped.
So when is the midterm actually?
Yeah, so the midterm will not be this the coming week. It will not be the following week also. It will most likely be in the last week of this this month. So let's just see. March. So this coming week is the week of 14th. The following week is the week of 21st, but the week of 28th. And in fact, we will. In fact, let me tell you, we will have the midterm during that week because we should not really postpone it too much.
So when did you
So I have, yeah. So notice that I have already now assigned you homework for the derivatives part. For and by the way, the problems that I have assigned you, some of these problems I will collect. The earlier problems, I hope you have written down all the problems in class, because the first homework will likely be due on the Monday following the midterms, because I want to give you the. I imagine that this weekend you will be busy studying for midterms. When is your last midterm next week?
So Thursday.
Thursday. Okay, so you will have a long weekend. Maybe I will make the homework due next Sunday, And that means that, and you will have at least 1 week. So you will get the homework before that for sure. Okay, so are there any questions? A question here. Suppose that U is convex, open in or whatever M, and there is a function f from U to Rn, and f prime of A exists and is bounded. And let us in fact say that, just say f prime of A equal to 0 for all A in. What do you guess about f? So the derivative of this function vanishes identically on this convex open set. What do you think is true about the function?
Sir, it's constant.
Okay, so then f is equal to constant. Why? Well, we saw that f of b minus f of a. So for all a and b in U, f of b minus f of a, its norm is less than 0 times b minus a, right?
Yeah, yes.
By the mean value theorem, right? So by MVT, a less than or equal to MVT from last time. Okay, so this was really a corollary that I forgot to state. The interesting question is, for what happens if U is open but not convex? Is the statement still true? Forget multivariable situation. Just think of ordinary functions. I have a function f from an open set of the real line to the real valued function. If the derivative is 0 at every point, does it mean that the function is constant?
No, we can have a disconnected interval as a domain.
Right. So if I just have, union of two intervals, two open intervals, let's say 1 to 2 and 3 to 4, and this function is defined on both, the derivative will be, derivative is 0 on each. But you see, the function is not constant globally, it can be locally constant, right? So somehow so if I want to have the same condition that this function to be constant, then somehow what I have to ensure is that this set does not break up into parts. Now, this is a notion that we have not discussed. If we have time, then we will discuss the notion of connectedness. So this is one of the exercises in is connected, then conclusion is again true. So if you want, you can think about this, but for that you will have to see what a connected set is. So we will see this later.
Sir?
We'll see later we have time. But we will try to make time. Yes, go ahead, please.
Yes, I was just saying that this means that convexity is like a stronger condition, and like we could so connectedness is like a sub condition of convexity.
Yeah, so here, example. Convex. I mean, including the interior, okay? Let's say the open interior of this, I'm not taking the boundary. It's convex. Whereas if I have something like this, the interior of this, open and connected, but not convex.
Right.
So somehow you can try to see, what would be the idea if you wanted to show that a function defined on this is with zero derivative is constant. Then you see the point is, if I take 2 points over here and here, I cannot really take this line segment to conclude, right? But this also suggests what to do.
Yes, sir. I can like take paths and like
Right. So basically, maybe you can always take a path going from one to the other. So the question is, what does connected mean? We haven't really defined it. So perhaps, should we include connected to mean that given any 2 points, then there is a path from one to the other? Then what do we mean by a path?
like a function from I don't know 0 1 close to the u where f of 0 is like the starting point on is.
Now you see, if I want to do this using the mean value theorem, then what you said will not really be so that's okay. So I mean, a weaker notion could be to say that that sort of piecewise linear connectedness, which is to say that if I should be able to do something like this.
Polygonal connect.
Polygonal, right? But the definition that you just gave, that is a more, at least seemingly more general thing, right? Where you can just take a curve.
If the curves are rectifiable, then it's equivalent to polygonal.
Right, but you see, here we don't really have to worry too much about it, because if I know that, see, what is going to be my hypothesis? My hypothesis is that if the function actually has total derivative at every point, then okay, so you see, if I want to apply mean value theorem, yeah, I'm going to be assuming that the function has total derivative at every point. Then that means that if I pre-compose it with but you see, here is the thing. No, sorry, I'm now getting confused here a little bit. Because you see, for the one variable mean value theorem, it is not enough to assume that the derivative exists at every point. I require.
So I think the one variable mean value theorem holds even if the derivative is not continuous.
Okay, sorry. So did I just make a mistake? I hope not. It's embarrassing. So no, I thought no. Okay, so this is, now you're confusing me, or rather, I am allowing myself to get confused here. That just oh, sorry. What am I saying? Yeah, of course. Yeah, it was a mistake in the lecture also, I said. So yeah, so what you mean is that you require continuity on the closed interval and differentiability on the open interval. Sorry, yeah, absolutely right. So that was my bad. Yeah, so then it is okay. No? Then there is nothing to be said, because if this function is differentiable everywhere, then by precomposing it with a smooth with a curve which is a differentiable map, you just apply the mean value theorem. Sorry, so that was a did I say this in the class? That was a major mistake. I apologize. Okay, so going back to the proof, what so going back to the proof, notice that the continuity of the partial derivative was used only at the last step. This is the only place where we use that the partial derivative is continuous. Until then, the only thing that we use was that the partial derivatives exist. Remember, all points are taken in the interior of this open set. So this continuous on the closed interval and differentiable on the open interval, I mean, that's neither here nor there. It's continuous and differentiable at all points because they are all points in the interior. Yeah.
Sir, if we have a connected open set, are we guaranteed that there is a differentiable path between any 2 points?
Right, exactly. So it's a good question. For open sets in Rn, I think so. In Rn, I think so.
Okay, sir. Okay.
Right. But no, I mean, so, I don't think of these things every day. I would like to say yes. It's a union of balls. In Rn, there is no issue, I think. So, okay, so here's what you kind of do. You see, a closed interval is compact, you see. So you can do something like the following. Roughly, so let's use the definition of connected as path connected. Those two things are somewhat different from each other in general, but for Rn, there is no issue. So that just means that there is a continuous path from one point to another. But if your set is open, then you see around every point on this path, I can put a ball totally inside this open set, no?
Yes, sir. And we can like sort of smooth it out and using
Right.
that ball.
Right. No, but the point is you have to do something, right? In that you have to use compactness. So finite number of these balls will cover. Right? And now you can have handover. So you see, between the first two open balls, there will be an overlap, right? So what you can do is, so right now what I'm giving you is I'm giving you something, well, for our purposes, something better than a smooth path, something better than a differentiable path. I am giving you a piecewise linear path. Because you see, if I have two balls and they overlap, then from the center of one to the center of the other, I have a path that consists of two straight line segments. Right?
Yes, sir. Yeah.
Just take a point in the intersection, just connect with a straight line and then just connect with a straight line. So I've given you a piecewise linear path. And for applying the mean value theorem, this is good enough to show, that the function is constant everywhere. So in fact, we just proved that if I have an open set which is path connected, in the sense that for any 2 points in that set, there is a continuous path from one to the other which stays totally inside the set. Then I can apply the mean value. Then I can do what I just did. Just get a path which consists of a finite number of line segments, and then use mean value theorem on each line segment using boundedness of the derivative to say that the function is constant from one point to the other, and just connect it all.
Yes, got it, sir.
Yeah. Please remind me in the beginning of the next class, because I think I made a wrong statement in the class, right? One of you did try to tell me that, hey, mean value theorem does not require continuity of the derivative, but I just plowed on like an idiot. So please remind me that I have to say this at the beginning of next class. I will also make a note in the lecture when I upload the and upload the notes. Yeah, so just to be clear once again, in the entire proof, the continuity of the partial derivatives was used, I mean, of the key situation where the target is one dimensional, the continuity of partial derivatives was used only at the very end. That's all. Before that, we did not need it.
Sir, can you repeat like what you just said? The proof. Yeah, if it is connected, then like
Oh,
the
sorry.
conflict.
What is your question? Is your question about the mistake that I made in class where I made?
No. Like, can you repeat the argument once
Right.
more?
So
Like, I did not.
I'll repeat the argument. But just humor me for a moment. Exactly where did I make the wrong statement? Because if possible, I will even delete it from the video. It's a bad idea to make wrong. So did I make the statement where I was using the mean value theorem? Is this where I made the wrong statement? That does anybody recall? Yeah, I think I made the wrong statement here. In that it is true that g is a continuously differentiable function, but the continuity of the derivative, because the partial derivative is continuous, but the continuity of partial derivative is not required. This appeal to mean value. Okay, right. So let's go back to the proof. So the idea is the following. So let me just say, we say that a set in Rn is if a set S, if for all A and B in S, there exists a continuous function from 0, 1 to S such that gamma, such that taking 0 to A and 1 to B. So claim, and I hope that this is correct, my proof is correct. If S is a connected open set in Rn, Rm, let's say, and f from S to Rn is differentiable on U such with f prime of A equal to 0 for all A in U. Then f of A is equal to constant. So let us attempt the proof here. The proof here is, so there is this set here, S, whatever, go. So the point is that from here to here, there is a path, right? So the path may be whatever kind of path, right? But let me try to draw this path in a, in a more, okay, perhaps I should. So the idea is the following. Okay, so help me over here. What do we want to do?
I think we can take covering of the path, which consists of
exactly
every point.
So right. So remember this is remember that this is, so forget the function. I mean, I'm not talking about the f. Really doesn't really play much role over there. It's just a straight use of mean value theorem over there. The point is, I can take so maybe use different color here. At every point of the path, I can put a ball around it. So here I can put a ball around P. And I can put a, and at every point, see, I cannot really draw a ball around every point, but here I can, maybe over here, the ball has to be small when it's, and like that. So I cover it with all of these open balls, all of which are stay totally inside S, because S is an open set, right? So for each point on the path, okay. Now really we should be careful over here. I'm talking sloppily. You see, a path is a function. So what does it mean to take? So what I'm saying is every point in the image of the path. So at every point in the image of the path, I put a ball around that, which is totally contained inside. So for all x in gamma of 0, 1, find ball of radius r around x inside S. Of course, r depending on S. So since gamma of 0, 1 is compact, so there exists finite subcover of this path gamma 0, 1 by, let's say, b of and now here is the thing. The notation becomes so no, this is, see, I mean, basically as you walk along the path, there will be some, right? So gamma by, no, that's by balls around gamma of T1, gamma of T2 to gamma of T, some large thing, some large n, right? Of radii, whatever radii, doesn't really matter. So basically, this is how the path is going to look, which I'm going to just draw it. You see, there is going to be something like this, 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 right? So what I'm going to say is that take A, which is in the first ball, then take the center of the second ball, and take the point in the intersection of those two balls. Remember that these two balls have to intersect. Okay, maybe over 1 second. Now I have to be careful over here. Why? So sorry, 1 second. Help me over here. Why should there be a handover point? No, maybe it will not come in order. The point is that this ball has to intersect one of the other balls. Okay, so sorry, I'm a bit confused here because you see, we don't really have.
Sir, if it is path connected, then it is connected.
Yeah, it is connected. That is true.
So otherwise, if we restrict it, we'll have a open.
Okay, a separation, right? So
yeah.
So I was trying to get by without using the definition of without using connectedness. The definition of connectedness, but even here it should be all right. See, yeah, no, I think maybe you are right. See, the point is that what should happen is that if I take the centers of all of these balls, then there should be a way of traversing from A to B. There should be an ordering of these balls such that A is in the first ball, B is in the last ball, and then any two of the balls overlap. Then what you can do is you can connect A to the center of the first ball. Then the center of the first ball to a point which connects it to something which is in the overlap of first and second ball. Then that overlapping point to the center of the second ball, and so on and so forth. You see, you have formed a chain of straight line segments. And remember, these balls are convex. So all of the segments will lie inside an entire ball. And therefore, all of the segments lie inside your set S. Now you run your mean value theorem. For each one of the segments, because the derivative is 0 at all points, the value of the function at the beginning point and the end point has to be the same. And then you go on like that. Okay. So maybe let me just check now, and you can say order these balls so that A is in the first ball, B is in the last ball, and any two consecutive balls overlap, that you have to give some kind of justification for that. But just using the path, it should not be difficult. But it's eluding me at the moment. And then use this gives a piecewise linear path from A to B, and then use MBT for each segment.
Actually, the ball might have radius 0 because consider the two squares which only shares one vertex and they are path connected, but not. Like you just give a ball argument here at the.
No. But you see, the point is my set is open. This is an open set.
Okay.
Right.
Yes. Sure.
Because you see, if I want the derivative of a function at a certain point, then the function has to be defined in the way I have defined it. The function has to be defined in the ball around that point, because I want to be able to take h small in any direction.
Yes.
So sorry, I'm not really able to complete this proof using just the definitions that we have, but the idea is correct.
So could we do something like this to show they have to be
Yes.
like overlap? Without loss of generality, we'll assume that the centers of two balls. So okay, maybe I'll say this better. We'll assume that our two balls are disjoint, but there is still a path between them, which stays entirely in one of the two balls. Without loss of generality, we'll assume the centers are minus a comma 0 and a comma 0. And we let the radii be, so the radius of each ball has to be
something. Yes, exactly.
Yeah,
and
no, my idea was.
And then you're going to use triangle inequality, right? There is going to be there is going to be a shortfall. Sorry, is that what you were saying, or you had some other?
Like that, sir. Yeah, like I was going to assume that, like in worst case, it wasn't fleshed out properly. I'll think about it more.
But okay, you know what? See, okay. So and I think that is perfectly fine, because my worry was that, or what I thought was a difficulty, is that you see the path that I have written, that I have drawn over there. That path doubles back, intersects itself, etc. But you know what? It doesn't really matter, because if my piecewise linear path also just goes back and forth, it doesn't really matter, no, as long as it is finite. So what we have to show is that each ball intersects at least one other ball. That is one thing. And I think the other argument that you were trying to do, that will be helpful over there. Because if some ball is not intersecting any of the other balls, then how can they cover the path? Of course, what I'm saying is not a proof, but there shouldn't be much to right.
Yes, sir. And I guess slightly stronger, I think we should be also able to say that if there is a path between two open balls, then they intersect. That feels like it really should be true also, at
Yeah.
least
So
in
what you're saying is that if there is a path that whose image contains a point in one ball and also a point in another ball, then those two balls have to intersect.
yeah.
Right? Okay. So good. That's a good statement to isolate, and that definitely has to be there, right? So, and remember, these are open balls, right? So in fact, the
Yes, sir.
intersection will have to be an open set, not just right. Okay. But if I have that, then how, you see, there is still some work to be done. In that, I still have to do some work to show that I go from A to B. You see, this should be all right, but I have a finite number of balls, and let us suppose that each one intersects with at least one other. That's not enough to connect, you see, because for example, I could have 4 balls, and the first to intersect and the second to intersect,
Yeah. Yeah.
but they are disjoint, right? So you see, so some kind of handover mechanism has to be there, which ensures that you go all the way from the beginning to the end, right? You see what I'm saying? That I do not have a situation like this. See, if I show that each ball intersects some other, then I could have something like this. That's not good enough.
Yes, sir. Yeah.
Right? So as stated, order these balls so that any two consecutive balls overlap. We have to get to this somehow. But anyway, you'll do all of this in point set topology. So so if you want to simply ignore what connected means, you will get to it anyway.
So, sir, maybe we can do something like this.
Yes.
So I take the first ball, and
What do you mean by the first ball?
like once you order these,
Okay, so you are taking are you taking an arbitrary ordering after choosing the finite subcover?
no, like your centers are in order from A to B.
Okay, so basically what you're doing is you're ordering the time points.
Yeah, yeah.
Right? Okay, so good. Okay, all right.
So I take the first ball and I
Yeah.
look at the path inside that ball, like intersecting with that ball.
Hmm.
I delete that part, and
Okay.
then I look at the rest of it.
Okay, all right.
So the rest of my path is again a path from some point A1 to B.
Yeah, so there is a minor quibble over here because my ball is open.
Yeah.
Right, so deleting the points from this is,
I mean,
right. I mean, you could delete maybe say something in the closure of this or something like that. But and also notice another thing. I mean, you see, you have to say this right in the sense that this ball. Okay, so here, let me just see your. So what you're saying is that this is the right. So now your path. So by the way, so this is at t equal to. So this is the first time point. Okay. You see, it need not be part of that. The point is that in this, some part of the path is there, but it may come many times. You see. So when you delete everything that is in here, you could be deleting lots of segments.
Yeah.
Right.
Okay.
Now you could say that you want to delete only the part that is the image of,
Like till it intersects the first time.
maybe what we should do is that here is the thing, don't cover the image of the path. Maybe what we should do is that we should take the inverse images of those balls, and this is good. This will now do the job. You see, okay. So this was the difficulty. The difficulty was trying to do this in the target space. Let's do this in the time space. You have this finite number of balls, right? Correct, in S. Take the inverse images of those. And choose a finite subcover of the time interval. Over there, you see my linear ordering will work perfectly. Because I can work with supremum and infimum and things like that, no? I have a finite cover of the closed interval. From that, I can extract a finite subcover which consists only of open line segments. Yes?
Yeah.
And that will do the handover for you. So this is the answer. This I think should work. Because you see, once you have a finite number of open intervals covering your closed interval 0, 1, then you can do the following. You can just take something that has the smallest infimum. Yes. And then take that interval. That interval will take you up until a certain point. The other endpoint of that open interval has to be also in one of the intervals. And you continue like that. So this will work.
Wait, why is the endpoint in another interval?
Because the endpoint is not in this interval. Remember, it was an open interval and I have a cover. If the first interval that you choose containing 0 is from A to B, then B has to be in one of the other open intervals, you see, because it's an open cover of the interval. So B has to be in something. And whatever interval B is in, of course, that will have to now overlap with the interval AB in a whole open interval.
Yeah. Because
Right?
B has an open ball around it.
Right, exactly. Yeah. So, okay, good. So, I really need to stop. So good luck with your exams. I'll put up these notes after making corrections, and get ready to work hard from Thursday onwards. All right. So I have already given you problems. I hope you've been writing them, including the ones given today. Then you will not have to work hard. But otherwise, you should really catch up. Okay, good. So let's stop for today.
Thank you, sir.
Thank you,
All
sir.
right. Bye.